My name is Ameet Pinto. I'm an assistant professor in the Department of Civil and Environmental Engineering at Northeastern University in Boston, Massachusetts. And my research groups looks at microorganisms in drinking water and wastewater treatment systems, how we can use these microorganisms to remove pollutants, and how we make sure that the water that gets to our tap is safe. In the United States, we use about 100 gallons of water on a daily basis. So we use this water for a range of different things, from washing our clothes to washing the dishes to flushing the toilet to drinking that water and bathing with it, and lots of other stuff like even watering the yard. But what we want to do is make sure that the water that we're using is clean, that it looks right, it smells right, it tastes right, and then it is safe for consumption, that it is safe for use. It does not have contaminants, whether they are chemical or biological, that can cause us illness, that can pose a risk to us. So how does this water get to our homes? Drinking water treatment plants typically use water from rivers or lakes or groundwater and then put them through a set of treatment processes so that the water that gets to us is clean and safe. And these treatment processes typically rely on a combination of physics, chemistry, and biology to remove a bunch of pollutants, all the regulated pollutants from the water supply. So what do these treatment processes look like? So for instance, one of the things that we need to do when we take water from the environment is remove the suspended particles. So you can imagine the leaves and branches in a lake. So you want to try to remove them. And the same for silt and sediment and rocks. So this is where physics comes into play. You're either filtering a lot of these suspended material out, or you are letting it settle by gravity. And so there are different types of reactors that are built for this. So one example might be that you might build a chamber that allows large particles to primarily settle by gravity. And we call these kind of chambers as primary sedimentation tanks. Another example of physical removal might be the use of filters to remove tiny little particles through a mechanism called size exclusion. So the tiny little particles get trapped inside the filter and only the water can pass through it. So those are two examples of where physics is used to remove large or even small suspended particles. Chemistry is also used during drinking water treatment. Sometimes there are these very, very fine little particles, or what we call as colloids, that don't settle out that easily, that are very difficult to filter out. So in that case, we use chemicals to try to aggregate these small particles so that they form larger particles, and then gravity can be used to remove these particles. So that process is called coagulation flocculation, and that is again followed by sedimentation. And this is one example of where we use chemistry. We also use chemistry in other cases to remove dissolved contaminants, for instance. You can use filtration columns that rely on adsorption, so there are charged surfaces on the surface of these filter media where these contaminants can stick to. And then you can also use chemistry to disinfect, to kill microorganisms before the water is sent out into the distribution system before it gets to us. Now, one example of where biology is used in drinking water treatment is where microorganisms are used to remove contaminants. And this happens by microorganisms essentially consuming these contaminants and growing on them. So the contaminants become the food source of the microorganisms. So those are examples of where physics, chemistry, and biology can be used to treat drinking water before it is distributed. Now, that's not the end of the road. That water needs to get from the drinking water treatment plant into our homes. So how does the water from there get to my home safely? So this is where we design drinking water distribution systems. This is infrastructure that you cannot see. It is hidden under the roads everywhere, but this conveys water through large and small pipes from the drinking water treatment plants, sometimes to water towers, which you can see, or sometimes to underground reservoirs. Again, you cannot see those, and then they can be pumped from there into our homes. And finally, then, we have fresh water at our taps. If you want to learn more about drinking water treatment, look up your local drinking water treatment plant. A lot of these treatment plants are enthusiastic to have visitors to give them a tour of their treatment process and educate the public about what the government does, what the local government does, and the water engineers do to make sure you have safe drinking water at your tap. You can also go to the website of your local water utility where they often describe these processes in quite extensive detail. You can also learn more about your water from the monthly water quality reports that most drinking water treatment plants are required to make public. So, for instance, in Boston, MWRA, the Massachusetts Water Resources Authority, makes a water quality report public every month. And so I can go take a look to see what the quality of my water looks like. You can find many more resources about water treatment and water quality. There are national organizations such as American Water Works Association, the Water Environment Federation, and all of these have local chapters that like to engage their communities in discussions and about water quality and to raise awareness about water quality issues. So these are great organizations to get involved with. Try to get in touch, send them an email, go to their website, look at what events they are planning in your neighborhood. And it's a fantastic idea to try to attend these. So you get to know more about water quality, and more importantly, you get to connect with water professionals in your neighborhood.